Yeah, you're right. Smart. You like basically
Yeah, it's like literally the same thing.
Yeah. I mean, I'm just but it sounds like yeah. So
Some of the
I don't think she hates you. I think she didn't like the class very much. Oh God.
nailed it.
Yeah, no, she had nothing to do with the course was, and I think she's taking a class about the course. I might be mistaken. She was like, yeah, I like the no, you're
By hand. Yeah, so he doesn't have to. Right, like when you run the agenda thing, it's not doing yeah, but if you do a no from
No, to the court. I'm saying the the mile by itself.
well, so you pass it and then that's it compares it all.
yeah, that's funny. That's exactly how I felt
So
about
you have a model that say has and it will add it. It starts with that there.
Alright, I'm going to start this thing programming,
Like
finding us all the way down here. It's a labyrinth down here. A couple of announcements before we have Yaron. Next week we have another seminar. Handling equipment to be taught you how to express yourself in art. Expressing yourself. 2 weeks later, April 25th, Spiros Mankoridis from Drexel. He will be giving the last seminar of this semester. And then we're going to start again next week. I hope you all found the flip is out there on the back. That's the most important part of this seminar. So it is a pleasure to introduce another friend from Yaron. And we can say, singer of Yaron. Yeah, I confuse it for anyways, he's an assistant professor here at Harvard. And before that, he received his bachelor from Tel Aviv University in Israel. Then he did his PhD another by another Greek at Berkeley. Using to Google as a postdoc. And then he has won awards. He was are Facebook, Microsoft. Okay. So today it's going to be talking about information diffusion through adaptive seeding. In other words, how not to have friends.
Okay, thanks, Pablo. Yeah, so very happy to be here despite the long distance travel. Maybe we'll make it without any jet lag. So today we're going to talk about information social networks. So think about this for the past decade, not century, people have been interested in understanding the way in which information diffuses in society. Really, so the understanding of the way in which ideas propagate from one individual to another. And starting in the 70s.
Can you speak up a little bit? It's hard to hear you. Sorry.
So I was just claiming that information diffusion in social networks is something interesting. And basically, starting in the 70s, sociologists have started forming mathematical models for what it means to propagate information from one person to another. And now when we have social data, we have things like Facebook, things like Twitter, or other companies that I didn't get a fellowship from, we can observe this kind of data and see and track exactly how it is that information diffuses from one individual to another. Probably what's more interesting for us as computer scientists or data scientists is that we can not only observe and learn these processes, but we can also engineer them. And this idea of engineering information or diffusion processes in social networks has been first posed by Domingos and Richardson, and later formulated by Kipling and Tarbush. And the formulation is extremely simple. So what we want to think about is we want to think about, suppose that we want to advertise a product or propagate some kind of idea, then how are we going to, how can we use a small subset of individuals who can spread that information effectively? Okay, mathematically, what that translates to is we say, let's say that we have a network that's represented as a graph, G. We have some sort of budget K. This is the number of rewards or the number of coupons that we can give to people if they agree to become early adopters. And then we have some sort of influence function. And what that influence function does is it basically quantifies how many people an expectation will we infect if we select a certain subset of people. Right? If we select a subset of people, we give them rewards, or we give them like a free iPod, right? Then what is the resulting adoption of that is going to be? Okay. So this can be quantified by this kind of influence function. And basically the question is, given this graph, budget, and influence function, then how do you select a subset of individuals of size almost k so that you're maximizing this influence function, this adoption? Does that make sense? So the nice thing in the Kempf-Tarbush model is that they reduce a lot of these diffusion processes to this kind of problem, and they showed that it's essentially that it's tractable. It showed that for a lot of diffusion processes, it translates into maximizing what we call a submodular function. That makes it approximate. So ever since their work, there's been really extensive follow-up work in algorithms and data mining, trying to basically better understand what these influence functions look like, and see if we could basically take a lot of data and basically fit information diffusion processes to these functions. And also, there's been a lot of work in algorithms trying to understand sort of the approximation guarantees that we can get for different influence models, and also coming up with better and faster algorithms for these kinds of tasks. So as a result, now we're more than 10 years later, we basically have this amazing arsenal of techniques for information diffusion in social networks. So why am I here? Okay, so the problem is that if you think about it, while all these techniques are really, really perspective, the data that they often work on is, so let's take a look at this graph here. And then what we can see here is this is the CDF of the Facebook degree distribution, okay, in logarithmic scale. The x-axis is the number of friends, and the y-axis is the percentage of Facebook users with that degree. So let's suppose that what we did is we did the following exercise. I'm going to tell you that I have 5 free coupons for free coffee at High Rise, which I wanted to get today, but I forgot. And I can award it to every one of you who will advertise this talk in your social network. Okay, so what would the result of that be? So my claim is that if I kind of looking around here, none of you are really influential. And I'm not saying that because I crawled your Facebook profile last night. Probably crawled some of you. But I'm saying that because essentially we're all sampled from a random graph or from a social network. Right? So if I look at, raise your hand if you have, let's say, more than 3,000 friends on Facebook. Is it more than 3,000 friends on Facebook? More than 4,000 friends on Facebook? So we have one. Raise your hand if you have more than 2,000. 1,000 should be easy. Okay. But now raise your hand if you know someone who you think is influential, or if you know someone who you think, even your friend on Facebook, who has on the order of, let's say, more than 3,000. Okay. So why is that? So if we think about this, right, basically, we're not very influential. The reason why we're not very influential is because we're all basically random samples from power law network, like the one that we see here. And what that means is, and power law networks have these very heavy degree distributions. So it's very common to see people who don't necessarily have a high degree, but people with a very high degree do exist, but they're just very, very rare, right? So in some case, we don't have a lot of friends, but we know people who have a lot of friends. And basically, the reason why we know people who have a lot of friends is because we're the endpoints of these people. Okay. So going back to sort of things that we care about, which is information diffusion, in most real-world settings, right, we don't just go to a social network and ask people to advertise for us or select people for a campaign. Right? The way that it goes is we usually have people either in a room, right, or we have people who visit an online store, or people who are targeted, or one form or the other. And usually when all these people that we have access to, they just don't have a high degree. Does that make sense? So what it is that we can do is, in 1991, Bell gave us this really nice theorem that's known as the French paradox. And that theorem says that in any graph, the average degree of a node is bounded from above by the average degree of a neighbor. Okay? It doesn't tell you this statement doesn't tell you exactly about how much, but it just tells you that the degree of a node is going to be small. The average degree of a node is going to be smaller than the average degree of its neighbors, where the average is over all of them. So I did this experiment where I generated a graph. Okay? And what I did is I selected all the nodes in the graph started off as pink. I selected 5 nodes at random, those are red. And then I selected, I selected 5 nodes at random, those are yellow. Their friends are orange, and their friends' friends are red. So the influence potential of selecting these 5 random nodes, but the 5 yellow random nodes is in red. Okay, and the rest is in pink. Does that make sense? And what I'm looking at the influence potential to see how, if I, instead of doing influence on people in this room, if I try to do something like influence on the friends of people in this room, how much exposure will I get? Okay. So the area in red quantifies the exposure. So this is one graph, and this is another. This graph had the same number of nodes, the same number of edges. And now, can anyone guess what the difference between these two graphs are?
We're selecting more like yellow.
Here we're also here we did the exact same experiment. We selected 5 yellow nodes. Their friends are in orange, and their friends' exposure is red. So I asked this once, and somebody told me the difference between these two graphs is the color. And I think that, and it's true, but that's not exactly what it means.
The yellow nodes are not selected randomly.
In both cases, they're selected randomly. Yeah.
The big number of connections.
Number of connections is the same. We have the same number of edges in both graphs.
Did you name the school?
Almost. That's good. Yeah,
On the left is truly random graph, and the right is a power distribution.
exactly. So Brandon went to back. So the graph on your left is a random graph where we just took every edge and we just connected between every 2 nodes at random. And the graph on the right is what we call a parallel graph, which is sort of the structure of what social networks, the degree distribution of social networks have parallel degree distribution. And this is the graph on the right. So in exactly the same kind of experiment, we would get, dramatic, the exposure that we would get on a social network versus a random graph. There's a dramatic difference. Right, so my point is, we can actually prove that while you're not likely to be very influential, meaning that if you select a person at random, their degree is going to be small, you're actually likely to know someone who is. Okay, the formal theorem statement there is that in parallel networks with constant fraction of random edges, we can actually prove that there's an asymptotic gap between the influence of the subset of random nodes and the subset of their neighbors. Okay. So really what we want to do is kind of leverage the structure that we have in social data and then kind of use that for better information diffusion algorithms. Right, so the standard approach in computer science is to kind of think about worst case. Think about the worst case graph. And the worst case graph is like the graph on the left. Which is there's no difference between selecting nodes versus selecting their neighbors. Right? But the fact that we know that we're working with social networks and that these social networks have this particular structure. And here, this is the power law degree distribution. And that tells us that we can really get asymptotic improvements if we optimize influence over friends versus optimize influence over the set of people that we have access to. Okay, does that make sense? Maybe this is a good time to take questions.
Yeah, so I was wondering, some social networks tend to only have like a specific niche or a community of people as opposed to being like more mainstream everyone joining. And would you ever be able to detect those characteristics doing these types of graphs, or would it not really matter?
So would we be able to kind of detect structural properties in social networks on these kinds of, when we were talking about these power law networks?
Yeah, like for example, if you had everyone from the school or like from the army or something sign up, they might have more defined relationship structures of who's connected to whom and who can do that.
Yeah, that's an excellent question. So, so basically the answer is yes. So the statement that the proof statement that I mentioned in the previous slide says that basically you can take any structure, take any social network that you want, whatever, whether it has a lot of communities, whether these communities are dense or not. And the only thing I'm asking is I'm asking you to promise me that that it's still going to have a power law degree distribution, and we have a definition for what that means, and that there is a constant fraction of edges that are random. If we don't have that, then we can show that we can't, that you don't have this problem. It's very easy to show. It's trivial example. So as long as I have these two conditions of small fraction of random edges and power law degree distribution, which sort of we believe that social networks do have, then this kind of theorem is going to hold.
So I'm thinking kind of difference between like Facebook and Twitter, let's say. Like I have friends on Facebook who friend me, and they have a lot of friends because they go around friending people. And I think most people will tend to probably not reject a friend request from someone who they vaguely know. Whereas on Twitter, for instance, I have to actively go and follow someone. So there's a much higher bar in terms of they're not asking me. I don't use Twitter, but I don't think that they're asking you to friend them. So I would think that like is the number of neighbors to a node necessarily a good indication of influence? Because someone could have a lot of friends while not being very influential.
You're right. You're right. There are different measures of what influence is. With the example that you gave on Twitter, so it's really the difference between having a directed and undirected graph, right? So we can kind of either remove all these edges, all these one-directional edges, and then kind of restate that theorem, right? Or we can agree on what it means to be influenced on these one-directional graphs. You're right. I mean, like there is. That is going to play a difference. Both in Twitter and Facebook, we see the power law degree distribution. So this kind of statement will hold. I won't get into this now, but at the towards further along the talk, I'll also show some results on real data and real social networks, just to kind of see this. Okay. But good. This is exactly sort of right. This exactly captures what it is that we want to do, right? So now that we're assuming that we can assume that the social networks have this structure and that friends have much higher degree, then our challenge is going to be how can we actually design algorithms that are going to leverage this phenomenon, right? How can we reach out to people and kind of optimize influence now? So to do that, I'm just going to give you like the simplest, the simplest idea that you could possibly think of, and then we'll try to formulate it. Okay, so the simplest idea of what you would do in this case is you can just say, well, how about we do this? Instead of spending all of the valuable 5 coupons for free coffee at High Rise, right, on people we have in this room, why don't we maybe spend 2 on Pablos and maybe somebody else? Wait for their friends to show up, right? And once their friends show up in the room, then we'll use the rest of the 3 coupons that we have, and then optimize influence over their friends. Does that make any sense? Right. The only problem that we're going to have is that we don't know. Pablos is connected to a lot of people. We don't know whether any of them is really how likely somebody is to come to Harvard or come to an online site and also be willing to spread the word for people. Okay, so formally this is what we call the adaptive seeding. Right, so so we're going to start with the same model that we have for influence maximization, for information diffusion, and that's just going to be we're given the graph, the social network, some budget k, and an influence function that we're going to try to optimize. Right. The difference is now going to be that we only have access to a subset of people that we call X. Okay, this is some arbitrary subset of people, and each one of their friends has some kind of probability of also be willing to become an initial adopter. Right, so I don't, Pablos has maybe 200 friends or maybe 100 friends on Facebook, and we don't know, and we're assuming that that we have some kind of probability for each one of Pablos' neighbors to also be willing to come in and spread the word about mental. Okay, so in this setup, we now have to sort of say what is our objective. So our objective is going to be simple. What we're going to do is we're going to try to make a smart decision in the first stage. We're going to try to select a subset of people on day one, so that in expectation over all the possible arrivals of their friends, we're able to maximize influence. Okay, so and that's what I have written up here. So we have the first stage where we have the subset X. This is the subset of people that we have access to. This is the people in this room, and then we have their neighbors. Okay, and for each one of their neighbors, there's some probability of them showing. Right. So what we're going to do is we're going to select the subset X. That's the algorithm, and we somehow have to quantify how good our solution is, or how good our choice of this subset is, right? And how do we do that? Well, we just enumerate over, supposedly, right? We enumerate over all possible realizations, right? And in every possible realization, right, there is a subset of people that I could have selected with the remaining budget that would maximize influence, right? So I'm basically summing up the weighted average of the optimal solution in every possible realization, and that's the value of selecting this subset S. Okay. So this is a kind of a stochastic optimization model, right? Where we make this initial selection, and that initial selection is going to affect the realizations in the second stage, right? If I don't select Pavlos, the people that are only connected to Pavlos will not see this, will not know that I'm giving a talk, and those realizations will never know. Okay. So sort of this kind of model has applications that are beyond influence in social networks, but what we're going to talk about is just influence in social networks. Okay. So obviously, kind of optimizing over this piece is hard, right? There are various ways to argue about that. One way is for the function that we're interested, even without any of these stochastic processes, this is an NP-hard problem. The fact that you're optimizing over all possible arrivals means that you're optimizing over exponentially many realizations. Right? All these things are very essentially they're computationally hard and they're hard to think about. And our gold standard is going to be able to get what we call approximation algorithms. So algorithms that we can prove that their solution is going to be some sort of factor away from this optimal benchmark. The whole goal is to get this factor to be as large as possible. So the question is, what kind of functions we can do adaptive seeding for? What kind of functions we can get good approximations for? The first result from last year, we showed that for any influence function in the triggering model, this is a class of functions that people work with in influence maximization, then we can give you an algorithm that gives you 10 approximations. So it's in the language of think about so this is really should be a 1/10 approximation, right? And where one is the best approximation that you can get. Okay. So that's considered to be a good result. And then this year we're showing that essentially you can extend that. You can show that for any submodular function, there's an algorithm which finds this is now a better approximation ratio, which is 0.39, 0.4, better than 1/10. This is an approximation of the optimal response. So the first result was kind of the first result where we introduced the model, we introduced the first kind of first ideas for developing these kinds of algorithms. The second result is uses different class of algorithms, but it does better. It does better it sort of gives you an approximation for any submodular function, which is a broad class of functions, and the approximation ratio is better. Okay. And what I'll do is I'll talk about the first result. So I'll give you some ideas for the first result. The second result, if you want we can chat offline. Okay. So the way that we're gonna what we want to do is basically we have this beast, we have this stochastic optimization problem. We want to somehow get a good solution. And the problem is that we have to do something that's what we call it is adaptive. So what the optimal solution does is the following thing. The optimal solution basically selects some subset on day one. It waits for the realizations of neighbors, right? It waits for publicist friends to show up. And then once it knows which friends showed up, then it says, okay, let's, and now let's take the rest of the budget and let's optimize over the friends that came, right? This is what we call an adaptive strategy. But it's very difficult to think about like how you're going to design an adaptive policy or an adaptive strategy, right? Because you basically have to tell me for every possible realization what it is that you're going to do. So instead, what we usually do is we think about non-adaptive policies, right? Where what we do is we say, I'm going to make all my decisions already on day one, without seeing any of the realizations. Okay? And doing that just makes it much easier to think about how to design these algorithms. So in this case, we can show that if we make all the selection of exactly which nodes we're going to select already on day one, then you can't get any reasonable approximations. Okay? So what we're going to do is we're slightly going to extend this idea into how we're going to design non-adaptive strategies with randomization. Right? So what we're going to do is basically we're going to do this very simple thing. We're going to select the nodes on day one, and we're going to select probabilities for day two. Those probabilities, here we use Qs, okay, where we're going to say, so for every one of publicist's friends, if they appear, then I'm going to select them with probability Q. Okay? And now our job is going to be to select nodes on day one and a probability distribution over their friends. Okay? So the way that we're going to think about designing this algorithm is the first thing that we're going to do is we're going to basically turn this into a concave optimization problem. We're going to draw a concave relaxation, and we'll show that in this concave relaxation, it actually is a good approximation for these randomized and relaxed policies.